Number 12 in the notes, I'm going to change a little bit the way we are writing our work equation. So we're going to have work, and then instead of the displacement, what we really need is the magnitude of the displacement, which is just a distance. So we'll do F times D and then cosine of theta, where theta is the angle between the force vector and the displacement vector. And we already talked about the fact that if the force and the displacement are in the same direction, the angle between them is 0, and the cosine of 0 is 1. You can check that with your calculator. And if the force and the displacement are opposite, the angle is 180 degrees from there to there. And the cosine of 180 is -1. And if the force is perpendicular to the distance, or the displacement, then the angle is 90 degrees, and cosine of 90 degrees is 0. And in this situation, no work is done. So the work will come out to be 0 because they are perpendicular. So let's do some examples, and you'll start to get a feeling for how this works. So in experiment A, which was our beanbag situation, so to remind us about experiment A, we lifted a beanbag, and the hand on the beanbag was an external force. And because of that, when it lifted through this distance, we had a transfer of energy into the system. So what we're going to do now is calculate how much energy was transferred into the system. So you're lifting a 0.25 kilogram beanbag up 30 centimeters by applying a constant force of 2.45 newtons. That is just the force of gravity on this beanbag. So if you calculated Fg equals mg, you would get this. And that's because we're lifting it at a constant speed. So our upward force has to be balanced with the downward force. So we want to find the work done, which is the energy transferred, because this is an external force. So we have a force, and then we also have a displacement, which is up. The angle between those is 0 because they're in the same direction. So then to find out how much energy is transferred, we have force times the distance times the cosine of the angle between them. Then we can substitute. The force is 2.45 newtons. The distance is 30 centimeters, and when you're working with energy, you really do want to convert to meters. You want to use newtons, meters, kilograms, those kinds of units. So in meters, this would be 0.3 meters times the cosine of 0 degrees. 2.45 times 0.3 times cosine of 0 is 0.735, which I'm going to round to 0.74 because this is two significant digits here. So 0.74 Newton meters. And this is actually a unit of energy. This is an amount of energy, Newton meters. It has another name, and so I'll go ahead and introduce that now. It is called a joule, capital J. So a Newton meter is equivalent to a joule, and this is joule spelled Joule. It says find the work done by this force. So we found the work done. It's positive. Positive means there's been a transfer into the system. And we want to know the change in energy of the system. Well, if this is the amount transferred in, then the change in energy of the system is just 0.74 joules. So it's an increase of 0.74 joules. Our second example. In experiment B, suppose you pushed horizontally with a force of 12 newtons for 35 centimeters. So example B was the toy truck. Okay, and we pushed to the right over some distance. So we're going to calculate now, and that was an external force, remember, because the system is only the truck and the floor and the earth. So this hand is not part of the system, and the force exerted by that hand is an external force. So it's going to cause a transfer of energy. So let's just sketch our force vector is this way, which is 12 newtons. And the distance is 35 centimeters, so converting that again, we would have 0.35 meters. And the angle between those is 0 degrees. So the work, FD cosine theta, and then substituting 12 newtons times 0.35 meters times the cosine of 0 degrees, and then calculating that, 12 times 0.35 meters times cosine of 0 is 4.2 Newton meters. And remember that a Newton meter is also called a joule. And it's positive, once again, and that tells us that the change in energy of the system is an increase of 4.2 joules. Okay, if the force is internal, then you're not going to get a change in the energy of the system, in that total energy. If the force is internal to the system, what's going to happen is some of the energy is going to change the way it's stored. It'll change from one energy storage mode to another one, but it would still be within the system. Okay, example 3. In experiment C, which was a bow and arrow, suppose the weapon, rather than a bow and arrow, was a slingshot, and you pulled it back horizontally. So the force is this way, with a negligible speed over a distance of 25 centimeters. So once again, these are parallel. And because a slingshot is like a spring, it takes increasing amounts of applied force to stretch it increasing distances. So when you first start stretching it, it's really easy to pull it back. But the farther you pull it back, the more force you need to use. So this is a situation where the force is not constant. Okay. The graph shows how your pulling force depended on the distance, and this should be centimeters over here. So we can see that when you pulled it back 5 centimeters, that required a force of 10 newtons. But by the time you got to 25 centimeters, it was requiring a force of 50 newtons. So we know the angle is 0 degrees because these are parallel, but we don't have just one value for the force because it's different for every distance. Well, what we might realize is that in our work equation, we're multiplying force times distance, and if you have a constant force, that looks like this on a graph of force versus distance, that at every distance you have the same value of the force. In that case, F times D is really just the area of this graph. Well, that gives us a way to handle situations where the force has a changing value over the distance. What we can do is we can find the area, and that will give us this value for the situation when the force is not constant. So let's calculate that. The area is going to be 1/2 base times height, and then we have cosine of theta, cosine of 0 degrees, which you might be remembering by now that cosine of 0 degrees is just equal to 1. So 1/2 base times height. The base is 25 centimeters. Remember to convert to meters, so 0.25 meters. And the height of the triangle is 50 newtons. Okay, so we're finding the area of the triangle here. And calculating that on your calculator, you will get 625 Newton meters, which equals 625 joules. So find the work done by this force. We found the work done, it's positive. And find the change in energy of the system, the energy transferred. So this is a positive amount of work. And then we have to ask ourselves, was it an external force? Well, in this problem, the weapon, the bow and arrow, or the slingshot in our new example, that was part of the system. The earth was part of the system, but the person is not part of the system. So this is an external force, which means it transfers energy. Because this is positive, this transfers 625 joules of energy into the system. So the system energy increases by this amount. Okay, example 4. Suppose you have the 0.25 kilogram beanbag on your hand and you lower it from 30 centimeters to 20 centimeters at a constant speed. So the constant speed is telling us that the normal force is equal to the force of gravity. And we actually know what that is from the previous example. So 2.45 newtons. So we know the force. Now let's look at the distance or the displacement. That is going to be down. Distance and how much? 10 centimeters. Okay, so converting to meters, 0.1 meters. And what's the theta in this problem? Well, the force is up and the distance is down. So that is an angle of 180 degrees. And the way you can always tell is draw a dot and put the force vector and the distance displacement vector on the same dot, and you can see the angle clearly that way. Okay, we're ready to find the work done. Work is FD cosine theta. The force is 2.45 newtons. The distance is 0.1 meter. The angle is 180 degrees. 45 times 0.1 times cosine of 180 is negative 0.245 Newton meters, which is negative 0.2, I'm going to round this to 2 decimal places, negative 0.25 joules. Okay, the force of the hand, this was an external force, right here. So that means that we have a transfer of energy in or out of the system. Because this is negative, this is a transfer out. So the system energy, total energy in the system, decreases by 0.25 joules. Okay, last example. Suppose you carry the 0.25 kilogram beanbag horizontally for 28 meters. Find the work done by the force of your hand on the beanbag and the change in energy of the system. Okay, so here I am carrying the beanbag, and my force is upward 2.45 newtons, and the distance is 28 meters. Now if you're thinking about the energy of the system, it's above the ground, so we have some gravitational potential energy, and it's moving, so we have some kinetic energy. I put some white out on here so it's not allowing me to write clearly on there. Now some later time, say after the 28 meters, we have the same system energy because it's not going any faster, hasn't been lifted or lowered, there's no friction occurring here, and nothing has been stretched or compressed. So if we think about it, we can tell that the total energy should have stayed the same, this being the same size circle as this one. So that means that the work should be zero. There should be no energy transferred in this situation. Let's see what happens. So FD cosine theta, the angle between these is 90 degrees. So substituting, I have 2.45 newtons times 28 meters times cosine of 90 degrees. And we're going to see here that 2.45 times 28 times cosine of 90 is 0, and that's because the cosine of 90 is equal to 0. So you really have 0 times 28 times 2.45. So you don't even have to do a calculation on this one, because you could realize in the very beginning that if the force is perpendicular to the distance, there is no work done and there is no energy transferred in or out of the system.